So
So do you think AI is turned on? What does it say? I don't know. It seems like it's not letting me do what I was able to do last time. I don't know. Every time is something different. Unbelievable. Well, it says meeting summary is on. I don't know. All right. Sorry about last time. I don't know what happened. And we were in this definition here. So it goes like that. Okay. Definition, Kassuratian, given two sequences f and g, the Kassuratian of f and g is the determinant w equal to fn plus 1, gn plus 1. Here f and g are linearly independent, hence f and g are linearly independent if and only if w is not 0. This means that if w, the determinant, is non-zero, then f and g are linearly independent. And if the determinant is 0, then f and g are linearly dependent. For example, so now we may write w parentheses f comma g to emphasize the dependence of w on f and g, okay? Because they depend based on these functions. All right, so we did, for if we take let's say g equals c times f. That means g can be written as a constant times f. Then w is fn plus 1. Now g is cfn and cfn plus 1. And you see that this is cfn plus 1 minus cfn plus 1, and that is equal 0. So the determinant equals 0, and you see if g equals cf, that means g and f are linearly dependent. So you can see they are linearly dependent. All right. Any questions? Let's take a look at our example from last time. Last time we took we had phi 1 equal 1, phi 2 of n is minus 2 to power n. Then w of phi 1, phi 2 is 1, 1 minus 2 to power n minus 2 to power n plus 1. And that is equal to minus 2 to power n plus 1 minus 2 to power n. And then if I factor minus 2 to power n, I'm going to get minus 2 minus 1. That is minus 3 minus 2 to power n. That is different from 0 for all n. Okay? So, of course, these functions are linearly independent.
Hey, Professor.
Yeah.
So is it right to kind of treat this like a Wronskian? Is that what this is?
Yeah.
Oh, okay.
Yeah, this is the Wronskian, but in the discrete case, they call it Kassuratian. Okay? You see, in the Wronskian, in the continuous case, this would be f prime g prime. Okay, in the continuous case. All right. Okay. Now, this can be the Cassavatian can be generalized to K functions. That is W of F1, F2, Fk is F1 of n, F1 of n plus 1, F1 of n plus k, F2 of n, F2 of n plus 1, F2 of n plus k, and the same thing, F1, F2, Fk to n Fk of n plus 1, Fk of n plus k. Okay? So this can be generalized to n function. All right. Any questions? Now, I want to take a look at let's consider the second order equation where is it? Okay, xn plus 2 plus b1 of n of xn plus 1 plus b0 of n xn equals 0, and for n belong to n naught. Okay. Then W of n, which is W of x1 of n plus 1 no, x1 of n, x2 of n, and this is by definition. Okay, is equal to W of n naught times the product of k equal n naught to n minus 1 b naught of k. Okay, so basically, whatever you do with it, and so this is Wn naught, whatever Wn naught you compute is, and so basically here is the proof. W of n plus 1 is equal to W of x1 of n plus 1, x2 of n plus 1, and that is x1 of n plus 1, x1 of n plus 2, and x2 of n plus 1, x2 of n plus 2. See what happened? And so that is equal to x1 of n plus 1, and then minus b1 of n xn plus 1 minus b0 of n xn. I'm solving for x1 n plus 2 in here. That's what I'm doing. And the same thing, x2 of n plus 1, and then I have minus b1 of n. This is x1, x2 of n plus 1 minus b0, x2 of n. And if you take the determinant, and simplify it, okay, so that is gonna be, after simplification, b0 of n times x1 of n, x2 of n plus 1 minus x2 of n, x1 of n plus 1. If you do all this and do correct calculation, and this is minus b naught, and so this is b naught of n. What is that? That is W of n. Okay? This one is W of n, which is W. This one is. Look at it. Okay? Because W of n is x1, x2, that would be x1 n, x1 n plus 1, x2 n, x2 n plus 1. Take the determinant, you'll get Wn. And you solve this, so you have Wn plus 1 equal to b0 of n, W of n. And this has a solution what? Remember, this is like xn plus 1 equal to an xn, isn't it? So this has a solution of Wn equal to a Wn naught, the product of k equal n naught to n minus 1 b naught of k. Okay? Any questions? Now remember, we have not learned how to find the solution yet, but we are gonna work toward that. Okay? So this is one of the identities. I'm gonna have to rewrite a couple of the equation. Recall, we had AK xn plus k plus AK minus 1 xn plus k minus 1 plus A1 of k x of, no, this is A1 x of n plus 1 plus a0 x of n equal to f of n. And that was 2 point, what did we call this last time? We gave it a name, 2.31. Okay, and its associated homogeneous equation is ak xn plus k plus ak minus 1 xn plus k minus 1 plus a1 xn plus 1 plus a0 xn equals 0. So this is associated homogeneous equation 2.3.2. Okay. Okay, so we have a theorem. Okay. Suppose phi 1n, phi kn form a fundamental set of solution of T.3.2. Then the general solution of T.1 is x of n equal x h of n plus xp of n, where xh of n equals c1 phi n plus c2 phi n plus ck phi k of n, and where is the solution of T.32 and xp is the particular solution of 2.31. Okay, so try to understand the theorem. It's like a differential equation. So what does it mean phi 1 and phi k and all the way down form a fundamental set of solution to 2.32? That means each phi solve 2.32, and the set phi 1 through phi k is linearly independent. This is what it means. Then the general solution of the homogeneous equation is xn equal xhn plus xp, where xh, this is called the homogeneous solution, is c1 phi 1 plus c2 phi 2, plus c2 phi 2 of n plus ck phi k of n is the solution of 2.32 and xp is the particular solution of 2.3.1. Next time, hopefully tomorrow, we will learn how to find xp. Okay? So for the rest of the day, we're gonna concentrate on how to find xh for today. Okay? So let's understand now, this is the solution. So the example, for example, let's take a look at, for example, let's say we want to solve xn plus 2 plus 3xn plus 1 plus 2xn equal 6. X of 0 equal 1, x of 1 equal minus 3. Okay? So it can be verified easily that each of phi 1 of n equal to minus 1 to the n and phi 2 of n equal to minus 2 to power n is a solution of the homogeneous equation xn plus 2 plus 3xn plus 1 plus 2xn equals 0. Moreover, phi 1 of n and phi 2 of n are linearly independent. So basically what I mean by that, W of phi 1, phi 2 is not 0. This is what we mean by that. Okay? I'm not done yet. I'm just giving you a second before I turn the board. How are we doing? All right? Okay. So thus xp, sorry, xh of n equal to c1 phi 1 of n plus c2 phi 2 of n. That is c1 minus 1 to the n plus c2 times minus 2 to the n. Okay? On the other hand, xp of n equals 6 satisfies the equation xn plus 2 plus 3xn plus 3xn plus 1 plus 2xn equals 6. You can check it. So you'll have, sorry, this is 1, not 6, 1. So you're gonna have 1 plus 3 plus 2, that is equal 6. You see that? Hence, by the theorem, the general solution is xn equal xh of n plus xp of n, that is c1 minus 1 to the n plus c2 minus 2 to the n plus 1. Okay? Now, we were given x0 equal 1, x1 equal minus 3. Okay? So let's see. So we have 1 equals c1 plus c2, and we have minus 3 equal to minus c1 minus 2c2. Okay? You replace n by 1. So if you add, you get minus 2 equal to minus c2. So c2 is 2. Okay? And now then c1 is 1 minus c2, 1 minus 2 equal minus 1. Finally, xn is c1 is minus 1, is minus times minus 1 to the n plus c2 plus 2 minus 2 to power n a plus 1. Any questions? I want you to understand that a lot of the student commit the following unforgettable sin, may I say mistake, which is they try to apply the initial condition to this, but this is only the homogeneous solution. So do not try to take the easy way out and apply the given initial conditions to find C1 and C2 from the homogeneous solution. So what you do, you hold off a little bit longer, find XP, and once you find the general solution, then you apply your initial conditions to find C1 and C2. Okay? Any questions? Because if you find C1 and C2 from XH, then C1 and C2 will not satisfy this equation. All right? Okay. I mean, in case this solution can be written as minus 1 to the n plus 1 and minus 2 to the n plus 1 plus 1. It can be written like that too. Okay? All right. Any questions? Okay. I do have an example, and I refer to the Okay, let me get my book here for a second. Consider the Fibonacci sequence, example 2.5. So I need to look at example 2.5. Example 2.9. Okay, 2.2. 2.4. 2.5. Okay, I'm gonna look back at example 2.5. This is called Fibonacci rabbit breeding. Fibonacci. Some people call it Fibonacci rabbit breeding. Or some people call it Fibonacci sequence. How many of you heard of that? Fibonacci sequence. All right. Fibonacci sequence occurs a lot. All right. Okay, let's see. Fibonacci sequence 3. Let me read the example. The problem of how many pairs of rabbit you will have after 1 year if you start with one pair and they each take 1 month to mature and produce one other pair each month afterward is illustrated through a calendar. This is a representation of the classic Fibonacci problem of reproducing rabbit. So basically, we're gonna take a pair of baby rabbit and put them into a field. How many pairs will there be at the end of each month and be at the end of 1 year? So there are some criteria. Rabbits are fully grown at 1 month and have another pair of bunnies at 2 months. Each pair is comprised of 1 male and 1 female, and no rabbit die or leave the field. And so this is the classic rabbit problem. This is the classic rabbit problem Fibonacci used to generate the sequence. So if we do that, you have 1, then we have 1, then we have 2, then the 2 become the 3, then 5, then 8, then 13, then 21, then 34, and so forth. And this number is going to be 55 and so forth. Okay, so look, the first number is 1. The second number, you look back and you get 1. For the third number is the sum of the preceding 2. For this one, for the 3, is 1 plus 2. For 5 is 2 plus 3. For 8 is 3 plus 5, and so forth. And this is how the sequence is formed. Okay. All right. So we're gonna let xn be the number of pairs at the end of n month, then based on the sequence, we have x at n plus 2, for example, here will be xn plus 1 plus xn. This is xn, this is xn plus 1, this is xn plus 2. That is xn plus 2. You see? Xn plus 1, this will be xn, this will be xn plus 1 every time if you switch. And now we have x of 1 is 1 and x of 2 is 1. Okay? Okay, we are going to be solving this equation later. So this equation will have to wait and we will solve it in a little bit. Any questions? So basically, this is another one called the Fibonacci sequence. So if you like to know what happened to xn after a zillion times, well, look at that. 34 is 13 plus 21. 55 is 21 plus 34. 13 is 5 plus 8. You see how it works? All right. So let us take a look at solving definite equation. All right. So we're gonna be working so we will be now solving 2.32. So we're gonna learn how to do it. And this is section 2.4. So this is section 2.4. We're gonna learn how to solve 2.32. Okay? Well, we're gonna assume we're gonna assume a solution of a solution xn of 3.2 of the form xn equal lambda to power n. Remember, in the continuous case, we took x of t to be e to the lambda t in the continuous case. See the difference? All right. And here, so this is a continuous case. We assumed xt equal e to the lambda t, and we found lambda. And here we have n belong to n naught. Then e to the k of xn is, you remember what that is. All right. That is xn plus k, isn't it? Because you apply it k times. That is the shift. Okay. Hence, 2.32 can be written as AK EK of xn, okay? I'm not trying to find my correct pages. Okay. Xn plus k, but xn plus k is lambda to the n plus k. Okay? Then this equation can be written as plus ek minus 1 e of n plus k minus 1 xn plus a1 e of xn plus a0i. This is the a0n a1 of xn equals 0. So this is again ak lambda to the n plus k plus ak minus 1 lambda to the n plus k minus 1 plus a1 e of xn of lambda n plus 1 plus a0 lambda to the n, that is equal 0. Now we're gonna factor lambda to the n. Lambda to the n. Yes. So this equation becomes ak lambda to the k plus ak minus 1 lambda to the k minus 1 plus a1 lambda plus a0 to power lambda to the k, lambda to the n, and that is equal 0. Okay? Since lambda to the n is never 0 for all n, we must have ak lambda k plus ak minus 1 lambda k minus 1 plus a1 lambda plus a naught equals 0. And I'm sure I give it a name, 2.43. Okay? Now, equation 2.43 is called the auxiliary equation that correspond to 2.32. Okay? In differential equation, what did you do? You consider cases, distinct root, repeated root, or complex root. Okay, that's what you did in differential equation. And we're gonna do the same thing here too. All right. Okay. All right. So next, we're gonna look at, so this is section 2.4.1. Okay. And it's called distinct root. Okay. So in this case, we assume lambda I different from lambda j for all ij equal 1, 2, all the way to k. There are not two lambdas are the same. Okay. All right. Any questions? All right. Remember the lambdas. So we have a theorem. Okay. If all the roots lambda I of 2.43 are distinct, okay, then okay, then each element of the set lambda 1 to the n, lambda 2 to the n, lambda k to the n solve 2.32 and the set is linearly independent. So the set is linearly independent. Okay. Then the general solution or xn of 2.32 is xn equal to I equal 1 to k lambda I to the n and ci. Let me rewrite it better. Is I equal 1 to n ci lambda I to power n. Okay. Oh, sorry, this is k. I equal 1 to k. Okay? Where the Ci, I equal 1 to k are constant. Okay? So they are constant. Any questions? So now, let us solve this one. I'm gonna call it 2.4.5. So let us solve this problem. Okay? Of 2.32, let me make sure I have my labeling correct. 2.32. Yes. Okay. All right. So let us. What time is it? 10:54. All right. So let's see how we can solve this problem. So we assume solution xn of the form xn equal to lambda to power n. Then here we have xn plus 2 minus xn plus 1 minus xn equals 0, or I'm going to have lambda squared minus lambda minus 1 equals 0. That is the auxiliary equation. Okay? What happened here is, you see, if you like, this is basically lambda n plus 2 minus lambda n plus 1 minus lambda n equals 0, or lambda 2 minus lambda minus 1 lambda n equals 0. And since lambda n is never 0 for all n in and not, we must have lambda squared minus lambda minus 1 equals 0. So we have this equation. That is your auxiliary equation. Okay? All right. Okay. So now what are the roots? Okay, I'm gonna erase this again. So we have the roots are lambda equal to 1 plus or minus square root of b squared 1 minus 4ac plus 4 over 2, that is 1 plus or minus square root of 5 over 2. Now I'm gonna stick to my note. Hence, the solution of, so let's take, I really don't care, the solution of 2.45 is xn equal to C1, 1 plus square root of 5 divided by n plus C2. It doesn't really matter which one you take, C1 and C2. Okay? All right. Now we know we have x1 equal 1 and x2 equal 1. So let's apply this to the solution. So I'm going to have 2 equals C1 times 1 plus square root of 5 plus C2 times 1 minus square root of 5 for n equal 1. And for n equal to 2, no, for n equal 1, I have 1. For n equal to 2, I'm going to have 1 equal to, or may I say 4? No, this is 2 correct, because I multiplied by the denominator. Okay? And 4 is C1, 1 plus square root of 5 squared, plus C2, 1 minus square root of 5 squared. Okay? So this is what we have. And if you try to solve this, we're going to have C1 and C2. You try to solve for the coefficient. C1 is a square, 1 over square root of 5, and C2 is minus 1 over the square root of 5. Okay? If you solve this equation. All right? Any questions? You can easily see.
Is the reason that you didn't try to find x of p because the equation's homogeneous, so you don't
Yes,
x of p?
yes, exactly.
Okay.
So XP is 0 here automatically. Okay? We're going to learn this tomorrow, how to find XP. Today, we're going to learn how to solve the homogeneous equation. Okay? Because the solution of the non-homogeneous depend on the homogeneous, as you saw from the theorem, depend on XH and XP. All right. So let's say if C2 is 1 over the square root of 5 plus 1 minus 1 over the square root of 5, because, and a plus 1, so this cancel, so equal to 2. I'm trying to justify it for you. You can do simple calculation and you can find C1 and C2. So, what is the solution? Xn is C1, which is 1 over the square root of 5 of 1 plus square root of 5 divided by 2 to power n minus 1 minus the square root of 5 over 2 to power n for n bigger or equal to 1. Okay? Notice xn is an integer for all n. This is the good thing about it. It's weird that, for example, remember the sequence was just a bunch of integers listed, right? And here you have a square root of 5. You have divided by 2. For example, you may ask yourself: is x10 x10 is an integer, and so is x9, x8. They're all integer. You see? So x10 will give you the location at when n equal to 10. Okay? So it's really funny. It's really weird, this Fibonacci sequence. So now if you want any number in the sequence, you just let n what n is, and we'll give you the number in the sequence, how it's listed. What about the rabbit population? And you notice the limit as n goes to infinity of xn is the limit as n goes to infinity of all that, that is gonna be the limit as n goes to infinity 1 over the square root of 5 plus 0, and that is gonna go to infinity. Because this number is 0. 1 minus square root of 5, because 1 minus square root of 5 divided by 2 is less than 1. Correct? Or may I say the in absolute value is less than 1. And this one is bigger than 1. And 1 plus square root of 5 divided by 2 is bigger than 1. So as n goes to infinity, this goes to infinity, this goes to 0. Okay? And notice that 2, this is 1, 2, the limit as n goes to infinity of xn plus 1 over xn, okay? And that would be 1 plus the square root of 5 divided by 2, and that is 1.618. And that is known as the golden ratio. This is the golden ratio. Okay? Any questions? All right, let's take a few minutes break and we'll come back, okay? Just about, let's make it 5 minutes again. I need to get a drink. All right, we'll be back in a few minutes. Hi, Lily. You don't want to say hi to the class? No? Okay. So now we're gonna do repeated roots. So this is the section 2.42, repeated root. Okay, I'm gonna go straight to the theorem. Okay. I'm gonna go to theorem 2.42. This is for repeated root. Okay. Suppose a root lambda of the characteristic equation or auxiliary equation auxiliary equation 2.43 has multiplicity j bigger than 1, then the root lambda contributes to the general solution of 2.32 the term C0 plus C1 n plus C2 n squared plus Cj to n j minus 1 lambda to the n. So that is the solution of that. Okay. Any questions? All right, so let's take a look at an example. Let's take a look at example 2.15. We have yn plus 4 minus 7n plus 3 plus 18yn plus 2 minus 20yn plus 1 plus 8yn equals 0. So this is the same as lambda 4 minus 7 lambda cubed plus 18 lambda squared minus 20 lambda plus 8 equals 0. Or this can be factors into lambda minus 2 cubed times lambda minus 1 cubed equals 0. So lambda equal to 3 has lambda equal to 2 has multiplicity 3. So its contribution is C0 plus C1 to power lambda plus C2 to power lambda squared times lambda to the n. Okay? And lambda equal 1 contribution is C3. Okay, lambda equal to 1, C3. Okay, so this is, let me finish this, C0 plus, no, I made a mistake here, guys. This is supposed to be n. C0 plus n plus C2n squared. So C1n plus C2n squared times lambda to power n times 2 to power n. And is C3 times 1 to power n, and that is C3. Okay? So the general solution is yn equals C0 plus C1n plus C2n squared 2 to power n plus C3. Okay, so that is the general solution. All the results are in the book. The proof of the theorem is a little bit complicated, but I would highly recommend that you take a look at it. It's in the book. Okay? Now we're gonna do complex roots. I may not be able to finish this today, but I'm gonna try. Complex roots. Okay? So we're gonna assume one root is complex. That is lambda equal to alpha plus or minus I beta, where I squared equal minus 1, or I is the square root of minus 1. Okay? So we're gonna assume one lambda, one eigenvalue, only one eigenvalue, because they come in pairs. They have complex now. Now recall that e to the t equal to n equals 0 to infinity t to the n over n factorial. And that is 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus t4 over 4 factorial plus tn over n factorial plus. Okay? So now we're gonna let t equal I times theta. So e to the I theta is 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the n over n factorial plus. And that is 1 minus theta squared over 2 factorial plus theta 4 over 4 factorial minus plus I theta minus theta cubed over 3 factorial plus theta 5 over 5 factorial. This. Because you see I theta comes from here minus theta cubed. This comes from here. This one comes from here. You see? And so forth. So that is cosine theta plus I sine theta. You always wondered where this formula came from, right? Well, that's what it is. Okay? So now we're gonna let rho is alpha squared plus beta squared, and theta is tangent inverse b over alpha. Then alpha from Euler formula we have alpha plus or minus I beta equal rho e to the plus or minus I theta, and that is rho cosine theta plus minus I sine theta. Okay? Now, so for constant C1 and C2, that particular part of the solution can be written as okay. Okay, I'm gonna rate this. Can be written as okay, this is gone. Can be written as xn equal to C1 alpha plus I beta to the n plus C2 alpha minus I beta to the n. And that is C1 rho e to the I theta to power n plus C2 rho e to the minus I theta to power n. We've already done that. C2 alpha plus beta is rho e to the I theta. Alpha minus I beta is rho e to the minus I theta. You see that? And that is rho n C1 e to the I n theta plus C2 e to the minus I n theta. Okay? Because if you replace this one, I n theta will be rho n cosine I n theta plus psi I n theta, and you will see what's going to happen. So this is rho n C1 plus C2 cosine n theta plus I C1 minus C2 sine n theta, and that is rho to the n C3 cosine n theta plus C4 sine n theta, and we took where C3 is C1 plus C2 and C4 is I C1 minus C2. There. So that is the solution, contribution of the solution. Okay? Okay? So that is the contribution of the solution. Let me take a quick example. So let's say I have xn plus 2 minus 2xn plus 1 plus 2xn equals 0, x of 0 equal 1, x of 1 equal to minus 2. So we have lambda squared minus 2 lambda plus 2 equals 0. So lambda is 2 plus or minus b squared 4 minus 8 over 2. That is 2 plus or minus square root of minus 4 over 2. And that is 2 plus or minus 2i divided by 2. And that is 1 plus or minus I. So alpha is 1 and beta is 1. So what is rho? Square root of alpha squared plus beta squared, square root of 2. So let's take lambda equal 1 plus I. So what about theta? Is tangent inverse alpha over beta. Is it alpha over beta or beta over alpha? Is it does, I mean, so that is tangent inverse of 1, and that is pi over 4. So now we can write the solution. So let's use this one. So xn is rho to power n. What is rho? Square root of 2 to power n. C1 cosine n pi over 4 plus C2 sine n pi over 4. Okay? And apply the initial condition, you get C1 equal 1, C2 equal minus 3. All right? But you notice here, you say, Dr. Raful, but you only took lambda equal 1 plus I, and that affects the angle. If I take lambda equal 1 minus I, the tangent inverse will be minus 1 over 1. So what does that mean? So that is 1 minus 1. So if you look at it, so you have 1 here and minus 1 here. So this is the angle. Okay? Or theta equal minus pi over 4. Okay? It's the same thing. Oh no, I meant this, sorry. It's this angle here, not the whole thing. It's this angle here. Okay? Minus pi over 4, or theta equal 2 pi minus pi over 4. Okay? So will be this way. That will be 7 pi over 4 pi minus. Okay? What the heck is that? Okay, so theta is minus pi over 4, and then when you write your equation, this will be cosine. The cosine minus alpha is cosine alpha, but this one will be C2, will be minus C2. But then C1 will be minus 1, C2 will be 3. So the solution will be the same. It doesn't really matter which one you take. All right? So I'm going to stop here, and I will pick it up next time. How's Lily? Lily's doing all right. And if you want to see it, hang on, but I will. Lily. 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 Come here. Let's go say hi to the class. Come. All right. Okay. Stop. All right. Can you come here? You want to say hi to them? There we go. All right. Now you saw Lily. She's alive. Okay, I'm going to stop recording. Email me if you have any questions.